In this video, we're going to look at the reaction of a ketone with bromine, first under acid conditions and later under basic conditions. Under acid conditions, the important thing is that the ketone is in equilibrium with its enol. This is true for all ketones. The equilibrium is not very great. The ketone is more stable, but there's always some small percentage of enol around. And so the first thing we do is we simply attack the carbonyl with a proton, and we get the protonated carbonyl. This is all set up to form the enol because we simply have to pop off this proton over here by using this CH bond to form the new carbon-carbon double bond. The carbon-oxygen double bond disappears, and we have our enol. Now this enol is basically a very electron-rich alkene because the lone pairs of the oxygen will donate in to the pi bond of the alkene, making it very electron-rich, which means that it's plenty nucleophilic to attack a bromine and extract a Br+. So we're going to have, the way this is going to work is the oxygen lone pair is going to come back, reform the carbonyl. This pushes this double bond out where it grabs the Br+, kicking out a Br-. So that is the bromination step. And of course we have back our carbonyl, so the only thing we need to do is to kick out that proton, and we have our product. This is a very straightforward reaction, a brominating a ketone. Now if you look here, it ended up on the more substituted side. So why did we brominate here and not there? Well, it's simply to do with the fact that when you form the enol, this is already a very reversible process, and thermodynamically, this is the more stable enol, and this reaction is slow enough that it can find equilibrium. So you end up brominating here on the more substituted side. So that's the bromination process that you get in acid. What about base? Well, base, it turns out, is a little bit more fun. So let me renew the page, and I'll change that proton to a hydroxyl group, and we'll do the reaction over again. Now, this starts off in a somewhat similar manner, except instead of forming an enol, we're going to form an enolate. So we're going to pull a proton off one of the alpha carbons. But which one? The more substituted one or the less substituted one? Well, it turns out in this case, the enolates that we form are so reactive that it becomes kinetically controlled. And so the methyl hydrogen is more accessible than the methylene over here. So in terms of kinetics, we're going to go for the methyl proton first. We're going to grab this proton, form a carbon-carbon double bond, push these electrons out onto the oxygen, and we have our enolate. And the enolate is going to be the key to this whole reaction because we mentioned that an enol was a good nucleophile. Well, the enolate is an extraordinarily good nucleophile. It's got a full negative charge on that oxygen, so it's really pushing electrons into the alkene. So we can draw a new reactive arrow. We need a copy of the bromine. And again, we're simply going to do a nucleophilic attack and grab that Br+. So we'll reform our carbonyl. Okay, the double bond will come around and attack the Br+, kicking out the Br-, and we'll have our brominated compound. Now this looks like we're finished, but we're not finished, and the reason we're not finished is, think about it for a second. That bromine is an electronegative element. It's not, the electronegativity of bromine is not all that great, but it's certainly a lot more negative than that of hydrogen. So the CH bonds on this carbon are actually more acidic than they were originally. So it's easier to form an enolate here than it was originally. So what happens, since we in base, is that we simply form a second enolate and at that position. And there's really no way to avoid it because those hydrogens are more acidic than they were originally. So again, I have to draw the hydrogen in here so I can take it off. So we're going to grab that hydrogen, form a new enolate, push the electrons out on the oxygen. Okay, and we have the second enolate, and let me just make this smaller. And the second enolate is all set up to add another bromine. So get another copy of the bromine over here. Okay, and we're just going to go and do this again. So again, we're going to come back, reform the carbonyl. The double bond is going to reach over, grab the Br plus, kick out a Br minus, and we have done a dibromination. Well, you can guess what's going to happen again. We still have that hydroxide, and this proton is getting even easier. It's even easier to pull it off this time. So there's the proton. We bring another modal base around, okay? And so you duplicate the base. So here's the base. We're going to go for that proton, form the double bond, electrons out onto the oxygen. Here's one more enolate for the show, and now one more modal bromine. Where's the bromine? Okay, one final bromination. Oxygen back to the carbonyl. Double bond reaches over and grabs the Br plus, kicks out a Br minus, and we now have our tribrominated product. Well, are we done? Let's just think about what would happen now in the presence of base. We have a couple things that we could do. We can't attack that same methyl group because it's totally brominated. There's no hydrogens left. What we could do is go over here and go for that hydrogen over here. But it turns out that's not what happens. That seems like a very reasonable thing to do, but that's not what happens. What happens instead, you attack the carbonyl. And when you attack the carbonyl, you form a tetrahedral intermediate, like we did in carboxylic acid chemistry. And this tetrahedral intermediate, well, it does what all tetrahedral intermediates do. It falls apart. But how does it fall apart? What is it going to do? Well, you reform the carbonyl, you got to kick out the hydroxide. Well, you could do that, but that's just going back where we came from. That's not very useful. Kicking out an ethyl minus is not going to happen because a negative charge on a terminal carbon is very unstable. It's not happy at all. But what about this group? If we kick out this group, put a negative charge on that carbon, it's actually stabilized by 3 electronegative bromines. And it turns out that works. You can kick out that carbon as an anion. And that's a little bit bizarre, but that's what happens. So we're going to come down here, reform our carbonyl, and we're going to kick out that carbon with 3 bromides. And that species, okay, is our ultimate product here. And let me just move things back on screen. We get this CBr3 and a carboxylic acid. Now the carboxylic acid, of course, is going to give up its proton like a shot to either the hydroxide or that Br3C minus that we just kicked out. And so what will the ultimate product be? Well, I'm running out of room down here. Let me just copy it up here. Our ultimate product is going to be the anion of the carboxylic acid, the carboxylate. Oh, come on. I don't know what I'm doing. There's our anion of the carboxylate. And this molecule here, when this picks up a proton, negative charge, of course, is gone. There's a proton on there. Let me just draw it in to remind you. This molecule here is called bromoform. You've heard of chloroform. This is bromoform, a methane with 3 bromines. Well, it turns out this reaction occurs very, very readily. If you have a methyl ketone, you go around, brominate the methyl completely, and then you kick off bromoform. This is called the bromoform reaction. You can do the same reaction with iodine. You form iodoform. You can do it with chlorine, and you form chloroform. And this only works, though, with methyl ketones. It's rather specialized, only methyl ketones. If this were not a methyl group, If this were ethyl groups on both sides, then what you would do is you'd brominate. We could only brominate twice if this was an ethyl group. And then you do indeed go to the other side and start brominating the other side. So if you had two ethyls, you'd put two bromines on the one side, then you put two bromines on the other side. But if you have a methyl, you form bromoform, and you don't brominate the other side. So that's a really wild reaction. It used to be used in the laboratory that we would use iodine to test ketones to see whether or not they gave a nice precipitate, which was the yellow compound iodoform, and it was a chemical test that you had a methyl ketone. That stuff's not quite so popular these days because we have good spectroscopic methods to do it instead, but it's still interesting chemistry. So I'm not sure that this would ever be very useful in synthesis, but indeed, if you had a reaction where you had a methyl ketone and you wanted to turn that methyl ketone into a carboxylic acid, this is one way you can do it by removing that methyl group. So it's kind of an interesting reaction. The mechanisms are kind of interesting. They're all very straightforward. This mechanism is long, but it's just, of course, the same thing 3 times. So I hope you are now a big fan of bromination of ketones.